Good morning, everyone. Welcome to our presentation. Today, we're going to explore an interesting and important topic in mathematics, exponents and powers. This slide is just our starting point, so I'll give you a quick overview of what we'll cover. We'll look at what exponents are, how to work with powers, and why they matter. I'm excited to get started, so let's dive in. Now, let's take a closer look at slide 2, which covers the question, what if the exponent is 1 or 0? This is an important concept because it helps us understand some fundamental rules of exponents. When the exponent is 1, the number stays the same because any number raised to the power of 1 is just itself. For example, 5 to the power of 1 is simply 5. It's a straightforward idea, but it's key to remember because it helps simplify expressions. Now, when the exponent is 0, things get a little more interesting. Any non-zero number raised to the power of 0 is always 1. So, 7 to the power of 0 equals 1, and this rule applies in most cases. This might seem counterintuitive at first, but it's a fundamental property of exponents that keeps the math consistent. Understanding these cases helps us simplify and work with exponents more effectively, which ties into our overall theme of mastering exponential expressions. Let's talk about what an exponent actually is. The exponent of a number tells us how many times we need to use that number in a multiplication. Think of it as a shortcut to writing repeated multiplication. It's written as a small number, positioned slightly above and to the right of the base number. For example, in 8 squared, written as 8(2), the exponent 2 indicates we multiply 8 by itself 2 times. So 8(2) equals 8 times 8, which equals 64. Sometimes, you'll also hear people call these powers or indices. Recognizing how exponents work helps us understand how numbers grow quickly, which ties into the larger theme of understanding mathematical patterns and operations. Now, let's talk about what happens when the exponent is 0. As you can see in the table, if you raise any number to the power of 0, the result is always 1. For example, 9 to the 0 power equals 1. This might seem a bit strange at first, but it's a fundamental rule in exponents that helps keep things consistent across different cases. Next, let's consider what happens when the exponent is 1. If you have a number raised to the power of 1, the answer is just the number itself. For instance, 9 to the first power is simply 9. These points are important because they show the basic behaviors of exponents at these key values. They help us understand the rules for simplifying expressions and give us a foundation to work with larger, more complex problems. Remember, whether the exponent is 0 or 1, the rules are straightforward but essential for mastering exponents. Let's take a closer look at this table of powers of 5. As you can see, on the left, we have different exponents, and in the middle, the expression that represents each power. On the right, the resulting value. Now, what's interesting here is that whether the exponent is positive, 0, or negative, they all follow a pretty straightforward pattern. For example, when the exponent is 2, we have 5 raised to the power of 2, which is the same as 1 times 5 times 5, giving us 25. When the exponent is 1, it's just 5, or 1 times 5. At 0, we get 1 because any non-zero number raised to the 0 power equals 1. Now, for negative exponents like -1, we flip the base into a fraction. So 5 to the -1 is 1 divided by 5, which equals 0.2. And for -2, you see it's 1 divided by 5 divided by 5, which results in 0.04. What this table really shows is that positive, 0, or negative exponents aren't separate or complicated ideas. They're all connected through a simple pattern. This pattern helps us understand exponential functions more deeply, and it's a great example of how the rules of exponents work consistently across different cases. This concept is fundamental as we explore more complex mathematical ideas later in the presentation. Let's take a look at some key laws of exponents with examples to see how they work in practice. First, consider the rule that when we multiply 2 powers with the same base, we add their exponents. So, 3 squared times 3 cubed equals 3 to the power of 2 plus 3, which is 3 to the 5th power, and that equals 243. Next, if we divide two powers with the same base, we subtract the exponents. For example, 6 cubed divided by 6 squared equals 6 to the power of 3 minus 2, which simplifies to 6 to the first power, and that's just 6. Now, an important rule: any non-zero number raised to the 0 power equals 1. So 9 cubed divided by 9 cubed simplifies to 9 to the 0, which equals 1. This is a fundamental concept because it helps us understand exponents as a whole. Moving on, when we raise a power to another power, we multiply the exponents. For instance, 2 squared raised to the third power becomes 2 to the 2 times 3, which is 2 to the sixth power, and that equals 64. And finally, there's a way to express powers of 10 in terms of multiplication. For example, 10 to the fifth power can be written as 2 times 5 to the fifth, which expands to 2 to the fifth times 5 to the fifth. This illustrates how exponents can also help us understand the structure of numbers. These laws are fundamental because they give us a consistent way to handle exponents, making complex calculations much simpler and more manageable. Let's talk about powers with negative exponents. When you see a negative exponent, it actually tells you how many times to divide by the base number. For example, take 8 raised to the power of -1. That means 1 divided by 8, which equals 1/8 or 0.125. So, a negative exponent indicates division rather than multiplication. Now, if you see something like 5 to the power of -3, it means we divide 1 by 5 3 times. So, it's 1 divided by 5, then divided again by 5, and once more by 5. This process is the same as dividing 1 by 5 cubed, which is 125. Therefore, 5 to the -3 equals 1 over 125, or 0.008. There's actually an easier way to think about this. Instead of doing multiple divisions, you can simply write it as 1 over the base raised to the positive exponent. So, 5 to the -3 becomes 1 over 5 cubed. This approach makes calculations quicker and clearer, especially with larger numbers or exponents. Understanding negative exponents helps connect division and powers, and it's a key concept in mastering exponents and exponential functions overall. Now, let's talk about using exponents to express small numbers in standard form. This is a really useful way to handle very tiny quantities that can be hard to write out fully. When we use exponents, we're essentially indicating how many times we multiply 10 by itself. For small numbers, we use negative exponents. For example, 10 to the power of -3 represents 0.001. This notation makes it much easier to read and work with very small numbers, especially in scientific calculations. It's a key part of standard form, which helps us communicate large or small values clearly and efficiently. So, understanding how to properly use these exponents is fundamental to mastering the presentation of numbers in science and engineering, tying back to our overall theme of simplifying complex data. Let's go through the questions on this slide. First, what is the value of 2 raised to the power of 5? Well, 2 to the power of 5 means multiplying 2 by itself 5 times. That gives us 32, which is option C. This illustrates how exponential notation helps us understand repeated multiplication efficiently. Next, converting a large number like 21,600,000 into standard scientific form. Scientific notation is all about expressing numbers in the form of a coefficient multiplied by a power of 10. In this case, 21,600,000 can be written as 2.16 times 10 to the 7th power, because moving the decimal point 7 places to the left gives us the coefficient 2.16. So, the correct answer is option A. Finally, let's look at the charge of an electron. The actual charge is extremely small, about 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 10 to the negative 19 coulombs. This is important because using exponential notation allows us to work comfortably with very tiny or very large quantities, which is quite common in physics. The correct choice here is option C. Overall, these questions highlight the importance of understanding exponential notation and scientific notation, especially in scientific and engineering contexts.